All right, so here we go, the swinging bar problem. So as promised, we're first going to do this in a fairly complicated way, but just to make a specific point. So let's say I have an infinitely thin bar, and to make our lives easier, we're going to pivot it at one end. So we don't know what's holding it in place there. Really can't tell, but something is just like pinning that in place. And this way is down towards the earth, right? And so what we're concerned with is this bar is going to swing through and eventually come to this position. I mean, it'll continue through that position and then swing back up this way. We're going to track the motion of the bar from here to here, and we may talk about some parts along the way, like for example, when the bar is at an intermediary position, but we'll do that a little bit later. So what I want to know is, the question is, how fast is the end of the bar moving when it is, being the bar, when the bar is vertical. So I'm actually looking for the tangential speed of this point at that moment in time. All right, so here we go. The way we're going to approach this is by looking at sum of torques. We can't look at sum of forces really, because the bar holistically is not moving. It's really important to understand here that the bar is externally constrained by whatever it is that pivot point is, whether it's a hinge or like an axle or whatnot. There is an external constraint on this. So the bar holistically is not going to translate because there's one point on the bar that's held in space, excuse me, or rather in place. So every other point on the bar is going to translate, but we definitely want to think about their rotation because the translation of all these points is different, but because of the mechanics of rotation of a rigid object, the rotation of all these points is identical. So by looking at the rotation and understanding the rotation, we can figure out what's happening to the translation of individual items. Because, for example, the final tangential velocity at that point is just going to be equal to whatever the final omega of the bar is times what the r for that individual point is. Right? Why talk about what's happening specifically to one point the entire problem when I can talk about what's happening holistically to the whole thing and then know about every point that's possible? So here we go. What am I going to do here? I'm going to start out by looking at forces. So what forces are acting on this? Well, the force of gravity is clearly acting on it. But here's the thing. Where am I going to draw the force of gravity? So I'm going to say that our bar is of uniform density. Let's say the bar is mass m and a total length of L, but it's uniform density. That's going to mean that I can put in the weight force for the entire bar at its center of mass. And that's so important. So this 1 Fg actually represents an infinite number of infinitesimal little Fgs. I don't want to have to integrate that, but this little dm has an Fg, this little dm has an Fg, I don't want to do that. I want to take the whole thing and say that that's acting at some distance here. Now we know that's L over 2 because for a uniform density object, we know that the center of mass is at the geographical center of that object. So I'm just going to draw that Fg force in here. Now, I will say that there are forces acting at the pivot here to hold that in place. We're not going to be concerned with those forces in this video because those pivot forces are going to act through the pivot point because they're pivot forces. And because of that, they're not going to provide any torque. Now, I'm just going to throw in some sort of F pivot. I'm not sure if that's the direction it acts or not. Like I said, there's another video that's going to talk only about those pivot forces so we can deal with it later. But none of them are going to cause torques at any point because of the fact that they act through the axes. So with that in mind, let's just say that this direction is positive, clockwise is positive. That's just going to make our lives a little bit easier here. So if I then do sum of the torques about that pivot is equal to I of the system about that pivot times alpha, well, what happens here? Well, this is just the torque due to gravity, and it's going to be positive, is equal to I about that point. Now, unfortunately, I have a bar not swinging about its center of mass, so I have to do a little moment of inertia problem here. I about that pivot, and I'm going to do this to the side, is I of a bar COM plus M of the bar D of the bar squared. So what's that? Well, that's 1/12 ml squared plus m, and then this is L over 2 quantity squared, and that comes out to 1/3 ml squared. In fact, if you just want to assert for a bar about its end that 1/3 ml squared is the moment of inertia from now on, you can, because that is such a common one that we're going to play with. So this ends up being I of a bar about its end, and then alpha. So let's put that in. So this ends up being just the force of gravity, so mg, its lever arm distance, which is L over 2, is equal to 1/3 ml squared alpha. And we can do some magic canceling. The masses cancel. And L cancels. And I get here that alpha is equal to 3/2 G over L. Okay? Now, that has some interesting implications. First, if I wanted to know what the tangential acceleration of the center of mass point is at this point, that's equal to alpha to r to the COM. So that's 3/2 G over L, and then r to the center of mass is L over 2, or 3/4 of G. But look at this. If I want to know what the tangential acceleration of the end point of this is, that's alpha r to the end. So that's 3/2 G over L, and to the end, that's L, or 3/2G. And that's really kind of trippy, that this point's tangential acceleration is greater than little g, meaning this point is going to fall quicker than if just the force of gravity was acting on it. So there's some interesting implications of that. For example, if I were to balance a coin on this end and then hold this in place and then drop it, like for example, if I had a coin here and I was holding this from here and I just let it swing, right? That would move out from under the coin faster and the coin would drop straight down, but that would drop away faster from it. Sort of a weird implication. There's another weird thing, is that there must be some point along here that is accelerating exactly at g. So what point is that? Well, if I look at that, so let's say g is equal to alpha, which is 3/2 g times r. Where is that? Well, that's at, this is going to be at, r would be at 2/3 of the distance out, 2/3 L out. So at 2/3 out, this point is actually accelerating at the acceleration due to gravity. I'll come back and talk a little bit later about some implications of that. But that's sort of weird that each point on this has a different tangential acceleration. Totally weird, but the same alpha. Now, let's say I want to know how fast this is going. Well, there's a huge temptation okay, well, I'll just use rotational kinematics, right? Because I have that object that's swinging from here and going to here. Okay, well, omega final squared is equal to omega initial squared plus 2 alpha delta theta. Okay, well, let's say it starts at rest. Omega final squared is equal to 2. I said alpha was 3/2 G over L, and delta theta, oh, well, that's how much it's swinging through. That swings through pi over 2, right? And so we can go, oh, half and half cancel. Omega final is equal to the square root of 3 halves G pi over L. Yay, done. Oh, plus or minus, excuse me, cross that out. Yay, I'm done, right? No. This is horror. Wretched. Why? Why? Stop the video and think about it. What is terrible about this? Hopefully, what you've determined is what's terrible about this is that alpha is not a constant. And we can only use rotational kinematics or any type of kinematics underneath constant accelerations. So let's discuss why alpha isn't constant. And to do that, we have to look at an intermediary position. So there we go. We're going to look at the bar when it's in this position, right? So that's what we're going to do on our next page here. So here we go. The bar is in this intermediary position. I'm going to draw the original sort of position that it was from. So it is rotated down a theta. Well, here we go. That is the force of gravity. We're not going to deal with the pivot forces there. I'm going to tell you they are no longer acting in the same direction that they were initially, but we'll come back to that question a little bit later. So if I go back once again to sum of the torques is equal to I alpha. It's just the torque due to gravity. This is still 1/3 ml squared alpha, but the torque due to gravity is different because the lever arm distance is different. As theta increases, hopefully what you see is initially this object's center of mass was L over 2 horizontally away, but as theta increases, this is going to get smaller and smaller. So what is the lever arm distance for this? Well, I think it's pretty simple to see now that if this is L over 2 down and that's theta, that this is L over 2 times the cosine of theta. Right? Just a little bit of geometry there. So that means I've got mg as my force. My lever arm distance is L over 2 cosine of theta is equal to 1/3 ml squared alpha. And once again, the masses cancel and L cancels. And then we get that alpha is equal to 3/2 G over L, very familiar, but times cosine of theta. So notice here cosine of theta, theta is initially 0 and goes to 90, so alpha is going to go from 3/2 G over L at cosine of 0 all the way down to 0 at cosine of 90. Now, I will tell you, there are some people who do this problem and they don't talk about the angle with reference to the horizontal. They'll talk about the angle with reference to the vertical and they'll define theta in this manner. And if they do, the cosine that we have here would be replaced with a sine, right? It's just changing the geometry because of using the complement. But that just depends on how you deal with this. Let's just deal with the way that I've defined the system with clockwise being positive and theta being measured from the horizontal. It's simplest for the problem that we have at hand. So now theta, or their alpha, is not a constant. So how on earth are we going to do this? Like, how am I going to find omega as a function of alpha? And hopefully that hand gesture let you know that what we're going to do is substitute, separate, and integrate, right? So notice here I have alpha and I have theta as my variables. So I need to do a substitution here. Remember, my possible substitutions here are d omega dt, because that's its definition, d squared alpha theta dt squared, right? Because that's a second derivative of position. But there's a third way of doing this, right? And it's the one we want because if I put this in, I've got 3 variables, omega, t, and theta. If I put this in, well, I've got 2 variables, but I've also got a second order differential equation, and woof, that's hard. So what is that other way of doing it? Well, if you remembered, by doing chain rule, I can do d omega d theta dt, and then I get d theta dt is just omega, so I get omega d theta. And there you go, that's what we're, the substitution we're using. So omega d theta is equal to 3/2 g over L cosine of theta. There's my substitution. Here's my separation. Okay, whoops, I don't need the, is equal to 3/2 g over L cosine d theta, and then I integrate. And I'm going to integrate from an initial omega to a final omega, and I know the initial omega is 0 because it started at rest. If it didn't, this would just be omega initial. And then finally, the way I've defined it, theta is going from 0, and the endpoint that I care about is when theta is equal to pi over 2. It's gone down to the vertical position. So this integrates into omega squared over 2 from 0 to omega, and this integrates into the integral of cosine as sine. So it's just 3/2 g over L sine of theta between 0 and pi over 2. So just going on to the next little bit there, move that out of the way, we can see that becomes omega squared over 2 minus 0 squared over 2, and then this is 3/2 g over L sine of pi over 2 minus 3/2 g over L sine of 0. That goes away. That goes away. I can get rid of a half there, and sine of pi over 2 just goes to 1. So omega final is equal to the square root of 3g over L. And that's it. So I now know that as that bar whooshes through the vertical, it's going at radical 3g over L. Therefore, if I wanted to know the tangential speed of the end point, that'd be omega at that final point times r, so radical 3g over L. I don't know why my radical is so long. And then L, that's how far that point is from the axis of rotation, so that's just radical 3gl. And that's the answer to our problem. If I wanted to know how fast tangentially the center of mass point would be going, that would just be 3g over L, and then times L over 2, and so that would just be 3/4 GL, right? So different points on that bar are moving at different speeds. So that's the terrible way of doing this. So I wonder if there's a way we can do this problem, but do it in about 1/10 of the work. Oh, that sounds like a really good idea to me, and that's what we're going to do in the next video.